Welcome back to Neural Intel. Today, we're stripping away the software layer and going straight down to the metal, or actually, the glass, that might just power the next generation of AI. Before we jump in, just a quick reminder for you. If you want the charts, the raw numbers, all the deeper analysis of what we're talking about, head over to neuralintel.org. And of course, if you're on the move, make sure you're subscribed on YouTube, Apple Podcasts, or Spotify so you never miss one of these deep dives.
It's great to be here. And, metal might actually be the wrong word for what we're getting into today. We're looking at a proposal that, well, it pretty much tries to delete silicon from the memory hierarchy.
Right. And we are unpacking a hardware proposal from John Carmack. And I feel like we need to set the context here right away because, most people hear Carmack and they just think doom.
Doom, Quake, maybe Oculus VR.
Exactly. They think gaming. But he's been focused on AGI, artificial general intelligence, for a while now.
He really has. And the thing about Carmack is that he is, at his core, a systems engineer. He doesn't just look at code. He looks at the physics of the machine that's actually running the code.
Yeah.
He has this reputation for finding the one bottleneck everyone else just accepts and asking, wait, why is this even here?
And the bottleneck he's going after today is memory, specifically the fact that our GPUs can do the math way faster than we can feed them the numbers.
The memory wall. It's the defining crisis of modern AI hardware. We have these incredible tensor cores, but they spend a lot of their time just waiting for data to show up from DRAM.
So Carmack's proposal is a pretty radical rethinking of how we store that data. He's suggesting we move away from traditional RAM and towards light.
A 200-kilometer spool of fiber optic cable.
When I first read that, I thought it had to be a joke. It sounds like something from a cartoon, but then I saw the numbers.
The numbers are sobering. He points to a demonstration of data rates hitting 256 terabits per second.
Okay, let's just pause on that. 256 terabits.
Terabits, yes, which converts to roughly 32 terabytes per second of bandwidth. To give you some perspective, the absolute fastest HBM3E stacks, the newest NVIDIA or AMD chips, they're pushing maybe 1.2, 1.5 terabytes per second per stack.
So this one fiber loop is offering something like 20 to 30 times the bandwidth of the most expensive memory silicon on the entire planet.
Correct. And that is just a single fiber strand with today's technology.
But I'm still trying to get my head around the form factor here. You said fiber optic. I'm picturing the cables running under the ocean. How does a cable become memory? I can't save a file to a cable.
You can if the cable is long enough. And this is the core concept of data in flight. Light travels at a finite speed. It's incredibly fast, but it's not instant. If you shoot a pulse of light down a 200-kilometer cable, it takes about 1 millisecond to reach the other end.
Which is an eternity in compute time.
It is. But during that 1 millisecond, the data isn't at the start, and it isn't at the end. It's literally occupying the glass. It is effectively stored in the journey itself. Carmack did the math. At 256 terabits per second, that 200-kilometer loop holds about 32 gigabytes of data in flight.
So the cable is the RAM stick.
It completely replaces the RAM stick. You'd have a transmitter on one end, a receiver on the other. You pump the weights, the parameters of your AI model into the fiber. They fly around the loop for a millisecond. They pop out into the processor's cache, get used for a calculation, and then they're immediately pumped right back into the loop to go around again.
It's a recycling loop.
Precisely. A delay line. And Carmack notes that while this sounds amusing, that's his word, it actually solves the physics problem that silicon is really struggling with.
Okay, let's dig into that physics problem because why is it easier to send light 200 kilometers through glass than it is to send electricity a few millimeters across a chip?
It all comes down to resistance, capacitance, and heat. When you're pushing electrons through a tiny copper trace at really high frequencies, you generate heat, a lot of it.
Yeah.
You get signal degradation, the skin effect kicks in, you just hit a physical wall where if you go any faster, the chip literally melts or the signal just becomes noise.
Electrons are messy, they bump into things.
Exactly. But photons are bosons. They can pass right through each other. They don't generate heat in the medium in the same way. And crucially, we have a technology called wavelength division multiplexing, or WDM.
That's the prism effect, right? Splitting white light into all its different colors.
That's it. In a copper wire, a signal is just a voltage. It's either on or off. But in a single strand of fiber, you can send a red signal, a blue signal, a green signal, and an infrared signal all at the exact same time, and they don't interfere. You can multiplex hundreds of these channels. And that's why Carmack thinks the bandwidth of fiber has a much steeper growth curve than DRAM. We can just keep adding colors. We can't do that with electrons.
So the bet is on photonics scaling faster than semiconductor fabrication. But there's a huge elephant in the room. You said a 1 millisecond delay.
Yes.
In the world of high-performance computing, 1 millisecond is a complete disaster. If my CPU has to wait a millisecond for data, my computer just freezes. You can't run an operating system on a 200-kilometer delay line.
Oh, absolutely not. It would be terrible for general-purpose computing.
So why does he think this is the answer for AGI? This feels like it brings us to our core technical segment.
Let's break it down.
Welcome to the neural signal check. This is where we stop looking at the hype and really get into the engineering reality. Why does a high latency system work for AI when it would fail for literally everything else?
It comes down to one critical difference between, say, running an OS and running a large language model. It's the difference between random and deterministic.
Walk us through that.
Okay, so when you're using your computer browsing the web or something, your CPU has no idea what you're going to do next.
Yeah.
You might click a link, you might open an app, you might close a tab. The memory access pattern is completely random and unpredictable. The CPU needs that low latency because it has to react instantly to whatever you ask for.
It's reactive.
Exactly. But a neural network is totally different. It's a giant, static mathematical graph. When you feed a prompt into something like GPT-4, the computer knows exactly what calculations it needs to do and in what order. Layer 1 feeds Layer 2, which feeds Layer 3. It's a fixed pipeline.
It's like a factory assembly line. You know that at step 50, you're going to need the bolt for the left wheel.
And you know you're going to need it exactly 10 milliseconds after the chassis shows up. Because the workload is deterministic, you don't need random access memory. You don't need the ability to jump around. You just need the data to show up at the exact moment the robot arm reaches for it.
So you time the flight. You launch the data into that fiber loop so it finishes its 200-kilometer lap and hits the L2 cache at the precise microsecond the GPU needs it.
Exactly. You turn a storage problem into a timing problem. Carmack's big insight here is that because we know the future, mathematically at least, we can completely mask that huge 1 millisecond latency. We just pipeline all the requests.
That's incredibly clever. It completely bypasses the need for all those complex memory controllers that handle random access.
And it removes the DRAM entirely. In this kind of architecture, you don't have memory chips. You just have the processor and the loop.
Okay, let's play devil's advocate. 32 gigabytes in a loop. That's small. My laptop has 32 gigs of RAM. The big trillion parameter models, they're terabytes in size.
That is the scaling challenge. And a single loop isn't enough. Carmack acknowledges this. He says you would need to pipeline a bunch of them.
So you're talking about a rack full of spools of fiber.
You are. And remember, 200 kilometers of fiber is actually physically quite small. The glass is thinner than a human hair. You could wind 200 kilometers onto a spool the size of a pizza box. So you could have a server rack with, say, 50 or 100 of these spools, giving you terabytes of capacity, all streaming at light speed.
That is such a wild image. A data center with no blinking hard drives, just banks of these optical spools humming with light.
It's a physics hack. It's using the properties of the universe, the speed of light, photon non-interference, to just bypass the limits of silicon manufacturing.
But as much as I love the sci-fi angle here, Carmack had a second proposal, one he called much more practical. And honestly, this is the one that feels like something a startup could build next year.
Yes, this is the pivot from pure physics to economics. He suggests that if we can't use light, we should just use the cheapest silicon we can get our hands on. Flash memory.
Flash, like the stuff in my USB drive in my phone.
The exact same technology. NAND flash.
But wait a minute. The whole reason we spend $30,000 on an NVIDIA H100 is because it comes with HBM high bandwidth memory. Flash is notoriously slow. It's orders of magnitude slower than HBM. Why would you pair a Ferrari engine with a bicycle chain?
Because the bicycle chain is basically free compared to the Ferrari engine. HBM is incredibly expensive, and it's very capacity constrained. You might get 80 or 140 gigs on a top-tier chip, but you can buy terabytes of flash for a few $100.
So it's a capacity play. But how do you solve the speed problem? If the GPU is just waiting around for the flash storage, it's sitting idle.
Carmack's proposal is to gang the flash.
Ganging it? You mean brute force parallelism?
Exactly. If one flash chip gives you, say, 1 gigabyte per second, then use 100 of them.
Right.
Or 1,000 of them. He argues you can achieve almost any read bandwidth you require if you just combine enough cheap chips.
Like a RAID array on steroids.
Yes. But, again, there's a catch. Flash is good at throughput moving big chunks of data, but it has terrible latency for small random reads. It takes a long time to wake up and find one specific byte.
Which brings us right back to our neural signal check logic, doesn't it?
It does. It relies on the exact same principle, determinism. Carmack points out that for this to work, you can't read random bits and pieces. You have to read a page at a time, and you have to pipeline well ahead.
So the system looks ahead at the AI model. It sees that layer 57 is coming up in 50 microseconds, and it tells the huge flash array to start fetching that data right now.
Correct. So by the time the GPU actually needs those weights, the flash array has already found them, bundled them up, and streamed them into a buffer. You completely mask the slowness of the flash by predicting the future.
This feels like it has massive economic implications. Right now, running a big model inference serving, it's so expensive because you need those high-end GPUs with all that memory.
And that's why he calls this the practical proposal.
Yeah.
Carmack says this should be viable for inference serving today. If you could build a box with a decent compute chip and, say, 10 terabytes of gain flash, you could run the world's biggest AI models for a fraction of the cost.
So, why aren't we doing it? Why isn't some company selling a Carmack inference drive right now?
Now we get to the bureaucracy of hardware. The bottleneck isn't physics, it's the interface.
The plug.
The protocol, really. Carmack notes this only works if flash and accelerator vendors could agree on a high-speed interface.
Okay, let's unpack that. What's wrong with the current interfaces? We have PCI Gen 5, we have fast connections.
We do, but think about the path the data has to take. Usually, flash connects to the CPU. The CPU reads the data into system RAM. Then the CPU has to copy that data over to the GPU's memory. It's a bucket brigade.
Too many middlemen.
Exactly. The CPU itself becomes the bottleneck. It just can't handle the sheer volume of interrupts and management to stream terabytes per second from flash. What Carmack is implying we need is a direct pipe, something more like CXL, Compute Express Link.
CXL is the big buzzword right now.
It is. We need a way for the flash controller to talk directly to the AI accelerator, bypassing the CPU entirely. We need direct memory access, DMA, but on a massive scale. The technology exists in pieces, but the standardization just isn't there. The flash guy is optimized for storage servers. The GPU guy is optimized for HBM. They haven't really sat down to build a unified inference interface.
It's like a classic coordination problem. The tech is there, but the handshake isn't.
And until they agree on that handshake, gang flash stays a theoretical architecture.
Yeah.
But if they do solve it, it could democratize AI. Suddenly, you don't need $1 million data center to run a trillion parameter model. You just need a whole lot of cheap flash chips and a really smart controller.
So we have these two really divergent paths. Path A is the fiber loop. It's high-tech, physics-based. It wants to replace DRAM with light. Path B is gain flash. It's low-tech, economics-based, trying to replace expensive memory with cheap storage.
But notice the common DNA there. Both of these proposals reject the standard computer architecture. Both of them are basically saying general-purpose computers are wrong for AI. A general-purpose computer is designed to be ready for anything, any click, any program. AI doesn't need that. AI needs a massive, predictable, relentless stream of data.
A slow-state machine.
Yes. And whether that flow comes from a beam of light or a bank of flash chips, the goal's the same. Feed the beast. Don't worry about random access. Just maximize the sequential throughput.
I think that's the big takeaway for you, our listeners, especially the engineers out there. We're still trying to run AI on hardware that was designed for gaming and spreadsheets. Carmack is showing us what hardware designed specifically for neural nets could actually look like.
You know, we're in the vacuum tube era of AI hardware. We're taking off-the-shelf parts GPUs, DRAM, and just hacking them together. The future architectures might look completely alien to us.
A 200-kilometer glass loop is definitely alien.
It is. But you have to remember the very first computers used Mercury delay lines. They used sound waves traveling through liquid metal to store data. That was alien too, but it worked. Carmack is kind of suggesting we might be circling back to that cyclical delay line concept, just, at the speed of light.
Which brings up a really interesting investment angle. If you're looking at the hardware space, everyone's obsessed with who can make the smallest transistor 2 nanometer, 1.8 nanometer. But if Carmack is right, maybe we should all be looking at photonics.
I would absolutely be watching the photonics space. If the bandwidth of fiber really does outpace innovation in DRAM, the value capture shifts. It shifts from the memory fab to the optical interconnect.
And on the flip side, you should watch the CXL space. Watch the companies building the controllers that let flash talk directly to GPUs.
That's the plumbing that's going to enable that practical revolution he's talking about.
So we've laid out the two visions, the fiber loop versus the ganged flash, physics versus economics. I want to throw this out to all of you listening. If you had to bet your R&D budget on one of these becoming the standard for inference in, say, 2030, which way are you going?
Do you bet on the speed of light, or do you bet on the cheapness of silicon?
Let us know in the comments below. We actually read them, and I'm genuinely curious if anyone out there has worked with these optical delay lines. I know they exist in things like radar systems. Drop some knowledge on us.
Yeah, I'd love to hear some of the technical feasibility takes from the optical engineers in the audience.
Definitely. And remember, for the diagrams of these architectures, because visualizing that fiber loop really helps, check out the blog at neural-intel.org.
It is worth a look.
I want to leave you with one final thought to mull over, something that really stuck with me from Carmack's notes. We tend to think of data as being static. It sits on a hard drive, or it sits in a floating gate in a flash cell. It's like a rock.
Right.
But this fiber proposal, it changes the fundamental state of knowledge. In that system, the data only exists because it's moving. If the light stops, the memory just vanishes.
Kinetic memory.
Exactly. Are we moving toward a future where our most valuable knowledge isn't written down, but is just a beam of light endlessly circling a glass track, kept alive only by its own momentum?
It gives a whole new meaning to the term live data.
It certainly does. Thanks for joining us on this deep dive.
Thanks for having me. Keep an eye on the hardware.
We'll see you next time.